Look up. That's not silence hovering above you right now. Something massive holds itself in the sky, harder than you'd think. Unlike other aircraft, this one refuses to glide. It claws through the air instead. Think of a ceiling fan at full speed. You trust it, but never stop to wonder what keeps that heavy spinning mass attached. Modern aircraft rely on redundancy, backup engines, backup computers. If one system fails completely, another wakes up and takes over the load. But inside early helicopter rotors, that logic simply didn't exist. One bolt, one single connection, no backup whatsoever, and absolutely no second chance. The rotor spins hundreds of revolutions per minute. The whole aircraft shakes, a controlled mechanical storm running just above the cabin. So here's the question that nobody standing on the ground ever thinks to ask. What exactly held all that violently spinning mass together? But look closer at that actual design and something simply doesn't match what any modern aviation safety standard would ever allow today. That single connection point wasn't a mistake at all. It was a deliberate compromise between physics, weight, and hard limits of available materials. 1965. A military airbase in South Vietnam. Mechanics are preparing a Bell UH-1 Huey under floodlights for a dangerous dawn mission. One technician stops at the rotor mast top, the exact point where every pound of lifting force converges into the airframe. Soldiers called it the Jesus nut. If that fastener let go mid-flight, the rotor detached, and the aircraft dropped like a stone. It wasn't just Vietnam. Gulf of Mexico offshore oil rigs, Rocky Mountain rescue crews, same single-point design, same concentrated risk, completely different context. Before every flight, the crew chief climbed up and touched that nut barehanded, using fingers to confirm the locking pin was seated. And it wasn't only the Huey. Bell, Sikorsky, and Hiller models all shared that same architecture. One central fastener, one mast top. Different squadrons. Alaska, Germany, Korea. One identical pre-flight ritual, repeated thousands of times every day across the entire American military helicopter fleet. Which forced engineers to answer an uncomfortable question. Why trust a multi-ton aircraft's entire survival to just one piece of threaded metal? Surprisingly, this system almost never failed on its own. Not in combat, not in extreme weather, not under years of constant operational pressure. Against every instinct you have right now, the Jesus nut held. So what secret actually kept these machines safely flying for decades? Engineers call it a single point of failure. One component breaks and everything collapses. No backup, no recovery, no way to survive. A helicopter tries to shake itself apart on every flight. The rotor generates a cyclic, rhythmic, relentless vibration. Every single bolt feels it. On the Huey, the rotor head nut sat atop the mast, holding the entire spinning assembly against constant torque and cyclic stress. Engineers drilled through the nut and mast, then threaded a heavy steel cotter pin straight through both. Almost too simple to trust. That nut could only come loose one way, by shearing through solid steel. Normal flight vibration simply cannot produce that level of force. No sensor tracked that pin, no computer monitored it. A crew member's bare fingers were literally the final line of defense before takeoff. Touch the nut. Confirm the pin. No computer, no sensor, just a bare hand. That was the safety margin before each flight. Even careful inspection missed one threat: metal fatigue. Invisible microscopic fractures building silently inside the fastener across hundreds of flight hours. Different engineering teams looked at this exact same problem and reached completely opposite conclusions about what the correct and safest solution was. How do you fix a critical failure point when physics demands all rotor load Concentrate at one single central spot above the mast. First school of thought: make that single point indestructible. Strongest alloys available, strict replacement schedules, mandatory hands-on inspection before every flight. This kept design light and simple, which mattered enormously in early rotorcraft, where every added pound reduced range, payload, and mission effectiveness. The second school argued, simplicity is wrong when stakes are this high. Use distributed independent bolts. If one fails, the others hold. Wartime logistics kept pushing toward simplicity. One visible nut is far faster to inspect in a jungle clearing than a multi-bolt assembly. Old system: lighter, faster to check. New system: heavier but fault-tolerant. Damage one bolt, the helicopter still flies. That trade-off took decades. Modern Black Hawk and Apache helicopters use redundant bolt arrays. The shift came not from disaster, but from deliberate redesign as materials advanced. But here's what neither engineering model explains. Why did the term Jesus nut survive long after the original design was permanently retired? Today, NASA engineers and Silicon Valley developers use that same term for any single dependency that can bring a complex system crashing down. Look at that helicopter again. Same sky, same sound. But now you see a decades-long argument between physics, trust, and engineering compromise. The Jesus nut is gone. But we still build systems with one piece that breaks everything. The part changed. The vulnerability did not. Subscribe for more. See you in the next one.